Hi, Year 12s. In this video, I would like to talk about the subtopic 11.3, which is integration with the aid of some trigonometry identities. And so far, we've done 11.1 across to 11.7. And before we get into 11.3, we'll just have a quick 1-minute recap on what we've learned in 11.1 and 11.2. So firstly, 11.1, we have acquired 9 standard intervals where we know the expressions on the right printed in green, ln x, sin x, minus cos x, tan x. When you differentiate that, it will give you these back. So these are all the standard intervals that we learned from our differentiation actually. And in 11.2, we take a step further, which is when we change the argument inside without changing the structure of that integral. For instance, the integral of cos 2x, the integral of sine x over 2, etc. and etc. You can see that these are all the same structure, so we can apply the same result, but all you need to do is to divide it by the coefficient of x. And these are what we call the f of ax plus b form, where inside the argument it is a linear function. It is an mx plus c function. So what is new in 11.3? So it is some new types of integrals that we need to learn, and it is not the same as the ones that we see from these standard integrals. So for instance, it will be an expression that looks, for instance, like this: the integral of sine square of x. And what shall I do first is that I will consider the double angle expression cos 2x. And now I would like to rewrite in terms of sine square of x. So as we know, cos 2x is cos squared x minus sine square x. And if I just want it purely in terms of sine square x, I will change cos square x into 1 minus sine square x as well. And then you will get cos of 2x as 1 minus 2 sine square of x. And you can rearrange and make sine square as the expression as a subject. You'll have sine square x as 1 minus cos of 2x all over 2. Okay? And then you can put it back into the integral. So the integral of sine square x can be rewritten in terms of cos 2x, which is 1 minus cos 2x all over 2. Okay? And then we will just concentrate to integrate that. So if you separate it into two, so you can separate into two fractions, and you have the integral of a half minus a half cos 2x with respect to x. And then you can integrate the half just using AS concept, so that will be a half x. When you integrate minus a half cos 2x, it's just like what we just did in previous slide. So when you integrate cos, you'll get minus sign. So minus a half of a half sine 2x, where you differentiate the coefficient, where you divide it by the coefficient of x as well, and you add c to it. And then you can further simplify it, and you get a half x minus a quarter sine 2x plus c. Okay? So as you can see, if we are going to integrate a square function, why do we do all of this? Is firstly, we couldn't remember, we don't know any integral of our heart, that when I differentiate it, then it will give me sine squared. So look at the answer, because remember, when I differentiate that, it should give me sine square x at the end. Okay, and it will take us a long way to even know the outcome without doing any manipulation first. So that's why you will need to use formulas to rearrange first, and then tackle the problem from there. Okay, so that's the example with the integral of sine squared x. We're going to use cos of 2x. Notice that whenever you see a square expression, and if the argument is x, then the identity, the cos identity that I'm going to use is always where we're going to double the argument. Okay, so if we look into another example, which is the integral of cos squared of 2x, and so in the first instance, the double angle formula that we're going to use is cos. Okay, and then we're going to double the argument, which is in this case we're going to use cos of 4x. Okay, so we're going to consider cos of 4x, and we're going to rewrite this using double angle formula, because cos of 4x is cos of 2x plus 2x, which you can use the formula booklet to rewrite it in a different form. So you will have cos squared of 2x minus sine squared of 2x. And then after that, you can rewrite the whole thing just in terms of cos squared by changing sine squared into 1 minus cos squared. And then if you just make cos squared 2x as a subject, you'll get a fraction. So cos of 4x is 2 cos squared of 2x minus 1. Make that as a subject, so you have cos squared of 2x equals to 1 plus cos of 4x over 2. And then you can put it back into your integral and finish the question. So the integral of cos squared of 2x will change into the integral of 1 plus cos of 4x over 2 with respect to x. And then you can separate into two expression again. So you have the integral of a half plus a half cos of 4x. And then you'll get a half x plus 1 over 8 sine of 4x. Okay? Any questions with that? Okay. All right. So here, as you can see, when we're integrating sine squared of an argument or cos squared of an argument, we're going to look into using double angle formula. So we'll use the cos double angle formula, and every time you're just going to double our argument. So in our first example, when it is x, I'm going to consider the cos double angle formula, but the argument that I'm going to use is 2x. Whereas if it's cos squared 2x, we're going to still use the same double angle formula, but the argument should be 4x. Okay, so that's why for this question, I'm not going to finish it. The third one, the integral of cos squared x over 2, we're just going to have the starting step, which is which formula should we use? We should be using cos double angle formula. And then in this case, since the argument is x over 2, so I'll be thinking of using cos of x. And then if I'm going to rewrite it using a double angle formula, so cos x is just x over 2 plus x over 2 as the argument. When you can change x into x over 2 plus x over 2, and then you can again write it into the expression that we want. In this case, will be cos x equals 2 cos squared of x over 2 minus 1. If you rearrange it, again, you have cos squared of x over 2 equals 1 plus cos of x over 2, and you can integrate from there. Okay? Now, another example that I want to go over will be an integral that looks like that. The integral of sine 2x cos of 2x with respect to x. So when you first look at it, Again, it is quite complicated, and we don't know. It is definitely not in the form of the integrals that we see in just 11.1 or 11.2. We know how to integrate these separately, but it is not correct if I just integrate sine 2x separately and cos 2x separately and multiply them together. Okay, so again, we need to think of using an identity so that we can write into a form that we can recognize. So instead of using cos double angle formula, when I see sine of 2x cos 2x, I can then consider first the double angle formula of sine. And in this case, the double angle, the argument I'm going to put is going to be 4x. Okay? Why? Because if we write as 2 lots of 2x for the argument, then you can use the double angle formula to change it back into 2 of sine 2x, cos 2x, and this is exactly what we want. This is exactly identical to the integral that we have, the expression inside the integral. And then what we're going to do is that we can divide both sides by 2, and we can use this expression as we please. Okay, so the integral of sine 2x cos 2x will again change using double angle formula into just the integral of a half sine 4x. Now, as you can see, after the transformation, then it is easy. Okay, we can just recognize the form that we will obtain, which is minus cos of 4x, and I divided by the coefficient of x, and finish the question, which will be a half times a quarter times minus cos of 4x, and that will be it. So far you could see that these integrals is just like the subtitle suggests. We'll be using different form of trigonometry identities, and so far we have been using 2 for different specific type of integrals. When you see that we're dealing with sine squared or cos squared, we'll be using the double angle formula of cos, and then we'll always double our argument. When it is a multiple of sine and cos with the same argument, then we'll still consider using trigonometry identity. In this case, it will be the sine double angle formula. And then once again, we're just gonna double the argument at this point. Okay, so we're just gonna double it. So that's why if we have a quick practice, the integral of sine of 3x over 2, cos of 3x over 2. So what expressions should we consider, or which trigonometry double angle formula we should use? So feel free to pause the video at any point to try the question yourself first. And in this case, we'll be using the sine double angle formula, and then we're going to double 3x over 2. So we're going to use sine 3x. That will be 2 sine of 3x over 2, cos of 3x over 2. So that's why the integral can be rewritten as the integral of a half sine 3x with respect to x, and then integrate from there. So 1 over 6 minus negative of 1 over 6 cos 3x plus c. Okay. And finally, I got 2 more examples to share with you, and that will be the end of 11.3. So there are two more types of integral. So for example, if I'm integrating cot squared, so we we'll aim to use a trigonometry identity so that we can rewrite it in a way that we can integrate it using the formulas that we have in 11.1 and 11.2. Okay, so there's only one trigonometry identity that involves chord squares. Okay. Okay, so feel free to pause the video again if you want to think about which one it is. Okay, so the one that we have should be cosec squared of 3x equals to cot squared of 3x plus 1. Okay, so cosec squared equals to cot squared plus 1, and then you can always just change your argument. And then in this case, you can make just cot squared 3x as a subject and substitute it into it. So the integral of cot squared 3x will be cosec squared of 3x minus 1. And then now you can see we remember how to integrate cosec squared 3x. That will be minus cot 3x, and I just need to divide it by the coefficient of x, which is 3. So minus a third cot 3x minus x plus c. So the very last one, we can just do it quickly. So there are two, so we're going to change it into using trigonometry identities once again, because we cannot put this into any it is not the format that we recognize from the formulas from the first session. So that's why we're going to use an identity to change it first. And as for tangent, there are only two identities. The first one will be sine squared over cos squared. As for the other one, it will be sec squared equals to tan squared plus 1. Okay, so it's the same case. So since the argument is 2x, so I'll put 2x in the brackets, and then I will make tan squared 2x as a subject. So that's why, and then we'll see why we should do this change. Okay, so as you can see here, we know how to integrate sec squared 2x. That is one of the form that we had. So that's why it will be a half tan of 2x minus x plus c. Okay, and then so far, as you can see, all the integrals that we have been dealing with is using various different A2 trigonometry identities that we've learned. The first two is the cos and the sine double angle formula, and then it is these reciprocal trigonometry identities that we have. Okay, which is cosec squared and sec squared. Okay, and once you have done the rearrangement, then within the integral, it becomes something that we can recognize, and then we can integrate just using the skills that we have been using throughout. Okay, so with these, you will be able to do question 1 from exercise 11C. Okay, and then so to finish this off, I'm just going to do the last question from question 2 in the same exercise. So the integral of cos 2x all over 1 minus cos squared of 2x with respect to x. Okay, so what can we do here? So firstly, 1 minus cos squared of 2x can be changed into sine squared of 2x. So I can change it into the integral of cos 2x over sine squared of 2x with respect to x. And then here we'd like to separate it into two fractions again. And then you can rewritten that as the cot 2x times cosec 2x, And actually, it's quite easy to do. It will give me minus a half of cosec 2x. That is disappointing. All right. Yeah, so as you can see, these are all we need to do, all we need to know for 11.3. Okay, so thanks for your time, and remember to do the work in 11C to consolidate on 11.3. And that's all I need to share with you. Thank you. Take care.